Hello everyone. In this section we look at sampling distributions and the center limit theorem. Here's some bullet points about a sampling distribution, and basically we're going to show that when we take a sample from a population, that the mean of the sample means will be equal to the population mean, and also that the standard deviation of the sample means will be the standard deviation of the population divided by the square root of n. So make sure you understand how to read the notation. When you're talking about a population, we use Greek letters, and we're talking about a sample, regular letters. For example, the mean of a population, we use the Greek letter mu. For sample, we use x bar. For the standard deviation of a population, we use sigma. And for the standard deviation of a sample, we use s. So get used to that. You don't really need to worry about this theory too much in terms of regarding solving mechanical problems. But here we're going to take a population that just has these three data values, 1, 3, and 5. And if we draw a frequency histogram of those three x values, so those are the data values, 1, let's say 2, 3, 4, and 5. Give myself a little more room here off to the right. And they just occur once. So 1 occurs once, 3 occurs once, and 5 occurs once. So it's a flat distribution, and that's what it looks like. Now if we take a sample of size 2 from this population, if you calculate the mean, it's going to be 3 in the sample, or excuse me, in the standard deviation, considering this population 1, 3, and 5, it's going to be 2. You could verify that on your own. If we take the samples of all possible samples of size 2 with replacement, we get 1 and 1, 1 and 3, 1 and 5, 3 and 1, 3 and 3, 3 and 5, 5 and 1, 5 and 3, and 5 and 5. Those are all the samples of size 2. Calculate their respective means, and then form the sampling distribution. What the histogram looks like now, actually we'll do a probability distribution. We'll do P of x, and this will be x bar because they're the means of the samples. And now let's say 1, 2, 3, 4, and 5. The probabilities, the highest one was 0.333, so I cut that in thirds, 0.222 and 0.111. So now 1 had a probability of 0.111, 2 probability of 222, 3 a probability of 0.333, 4 0.222, and 5 0.111. So this sampling distribution, this is the sampling distribution of the sample means, and it's starting to become normal. And it turns out that we'll have some properties on the next page that talk about the sampling distribution of the sample means in particular with regards to the sample size. But what we've illustrated, and you can calculate these, is that the mean of this sampling distribution of the sample means, because that's what we just created, if you calculated the mean here, you'd get 3. So the mean of the sample means is 3, which note is the same as the population mean. And the standard deviation of the sample means it's 1.4, etc. But it's just the standard deviation of the population divided by the square root of n, or the square root of 2 in this case. So we've illustrated those properties that are summarized there. Now if we go to the next page, we see the center limit theorem stated formally. basically says if you take samples of size 30 or greater, 30 is the magic number, from any population, doesn't matter what the population looks like, then we're going to have those characteristics that we talked about, and the sampling distributions will approach a normal distribution. And the bigger the sample size, the better the approximation to a normal distribution. But then if the population's already normal to begin with, then the sampling distributions of the sample means it's going to be normal no matter what the sample size is. But in either case, we have those two characteristics that we just theoretically illustrated, that the mean of the sample means is mu, and the standard deviation of the sample means is sigma over the square root of n. So now it tells us that our formula z for a sample mean is now going to be x bar minus mu over sigma divided by the square root of n. So notice the difference between the two formulas. Let me break out some scrap paper here and state this for us. The difference is when we want the probabilities, involving, let's say, individual data, like we've done in the past, we're going to use that standard z-score formula, x minus mu over sigma. But if we're talking about the probability of a sample mean, that's our central limit theorem. And the z-score formula changes because we're talking about a sample mean. It's going to be x bar minus mu over, this would be, as we wrote, sigma over the square root of n, but that's really the standard deviation of the sample means, as we noted here. So divided by the sigma over the square root of n. And this is illustrated on your formula sheet. If you look at chapter 5, formulas, we have our standard z-score formula, which is x minus mu over sigma. But then if we talk about the central limit theorem, they talk about all the characteristics of the central limit theorem, but then as you can see here, they describe it, and I would use this final version, x bar minus mu over sigma over the square root of n. So that's when we're talking about the mean of a sample. So make sure you know when we're talking about the mean of a sample and when we're just simply talking about individual data. So the first example here just has to deal with these two characteristics about the mean of the and standard deviations of the sample means. We're given here that the city has a mean, the phone bills have a mean of 64, so assume that's a population mean, 64. Similarly, the standard deviation is 9. Population standard deviation, sigma, would be 9. And tells us we're going to get a random sample of 36 phone bills. So that's the value of n. We're taking sample size. Our sample size is 36. And they want us to find the mean and the standard error of the mean of this sampling distribution. Well, the mean of the sample means, which we notationally indicate by mu sub x bar, is the mean of the sample, is the mean of the population, which in this case was 64. So that's going to be the same. But then the standard deviation of the sample means, which we indicate by sigma sub x bar, is the standard deviation of the population divided by the square root of n. So the standard deviation of the population was 9 divided by the square root of n, which was 36. And that calculates to be 1.5. So when we go through the next example, we're going to see how to mechanically deal with the two different situations of either talking about a mean of a sample or the mean or an individual piece of data. First off, the givens. Okay, so here it tells us the annual salary, normally distributed. Here's the mean and standard deviation. So just keep in the back of our minds, we're normally distributed. Mean is 59,100, so that's mu. Sigma is standard deviation, 5,000. Take a random, part A here, we take a random sample of 35 nurses. So therefore, n is 35. We want the probability that the mean of the sample is less than 57,000. So notationally, we would write the probability that x bar, the mean of the sample, is less than 57,000. And if we're talking about the mean of the sample, then we're going to use the central limit theorem. And our z-score formula is going to be x bar minus mu over sigma divided by the square root of n. Okay, so that's very important to understand what z-score formula we need to use, and it's simple enough, the fact we're talking about the mean of the sample. Now if we draw a picture, let me do it off to the left here. If we draw the actual normal distribution, the mean of the population, mu, still goes down the middle. That's your 59,100. Our critical value, or the value of interest, is 57,000, but that's x bar. So to the left, we should label that as x bar is 57,000. And we want everything less than that, so that's everything to the left. So shade in that tail. Now we're going to transform to z-scores. We already know the z-score for the mean is 0, but we're going to have to calculate a z-score for 57,000. So for x bar again, equaling 57,000, our z-score formula, once again, we restate it, x bar minus mu over sigma divided by the square root of n. So our z-score formula is the 57,000 minus the 59,100 over sigma was 5,000 over the square root of n was 35. Now make sure you can calculate this. If you want to do the numerator and denominator separately and then do the division, that'll work, but here's the way you could do it in one sequence. Just make sure you type in 57,000. This is not the only way, but you could do it. I'm going to show you one way you could do it. So you type in the 57,000 minus your 59,100. Make sure you press equals before we do the division. But then after we hit the division key, make sure that you open up a set of parentheses. Okay, so that's crucial because you got to do another division in the denominator. So the parentheses after the first division is necessary. And then I can continue with the 5,000 divided by, hit second function, square root of 35. If you want to close up, double parentheses, parenthesis for the radical, and parenthesis for the division, and then press enter, and we get negative 2.48 rounded to the nearest hundredth, which we know we want to round to the nearest hundredth because we're dealing with z-scores. So this z-score is negative 2.48, and we're looking for the area or the probability. I always just say area. You could say the probability of x bar is less than the 57,000 if you want. But that's actually just going to be the area that we find in Table 4. Because recall, of course, Table 4 gives us the left cumulative area. So you should be familiar enough with it, but just to show you one more time, where are we? Negative 2.48, so negative 2.4, intersect that with 0.08, and it looks like 0.0066. So that is our actual area or probability. Okay, but now here's the difference if we're talking about a single registered nurse. So since we're talking about an individual piece of data, then it's just our standard z-score x minus mu over sigma. And we still just want, or I'll say need, the probability that x is now less than 57,000. So notice the difference. Here we're talking about a sample mean, had to use the central limit z-score formula. Here we're talking about a single piece of data, so our standard z-score formula. So you could draw the picture again. And we get our normal distribution, of course, mean going down the middle, which is the 59,100. But see, the 57,000 now that's to the left is not x bar, it's just simply x, an individual piece of data. We still want what's to the left, and that's going to be the area that we look up in the table. Oh, I forgot to label it here. I just looked it up, but I could have labeled it on the graph, 0.0066. But here, we'll now say for x equaling 57,000. Now we're going to use the z-score formula, x minus mu over sigma. So that gives us the 57,000 minus the mean, 59,100 still, over standard deviation of 5,000 still. And the z-score formula there calculates to negative 0.42. So then we look that area up in the table, and you find 0.3372. That's what we're looking for. Again, your choice as to how you want to state this. I always like to say area, but you could state that the probability that x, again, is less than 57,000 is going to be that value of 0.3372. Okay, so we got a couple more to practice. But look for this concept of the sample mean. And in example 3 here, we've got the length of time people spend driving, normally distributed. Keep that in the back of our minds, of course, typically stated all the time. See, when it's normally distributed, you don't even have to worry about the size of the sample n. But here's the given, once again, off to the side. The mean is 43.9, so that's mu. So you want to make sure you associate the right symbols, obviously, with the given data. Standard deviation, 5.8. Those are the two things that are always going to be given, right? Because that describes the normal distribution. we want the probability. We randomly select 50 drivers. So n equals 50. What do we want? We want the probability that the mean time they spend, the 50 drivers, or the sample mean, is between 42 and 45. Okay, so this one, we've got to state that 42 is less than x bar, which is less than 45. Okay, so let me reinforce the fact that, again, we're talking about a sample mean. So that's our central limit theorem and our special z-score formula, that z is equal to x bar minus mu over sigma divided by the square root of n. Okay, so we've got to do it twice. Let's draw the distribution first. So it's normally distributed. Mean goes down the middle, was 43.9. Got two critical values, 42 and 45. 42 somewhere to the left. That's x bar though. 42 and 45 somewhere to the right. And again, it's x bar. We want everything between. Okay, when we calculate these z-scores, again, we're going to get the left cumulative areas. So I'll draw these arrows as normal. And we'll fill in the areas when we find them. But we're going to change these to z-scores. So we got z equals 0 for the mean, and then the two z-scores that we're about to find. So, first one, for x bar equaling 42. Okay, again, the z-score formula we need to use is the central limit theorem, because we're talking about the mean of a sample, x bar, and so therefore the formula, once again, on our formula sheet, as we noted, x bar minus mu over sigma divided by the square root of n. So our z-score formula here gives us x bar is 42 minus the mean 43.9 over the population standard deviation 5.8, and then divided by the square root of n, which was 50. And if we crunch all that down, we get negative 2.32. And then we look that up in table 4. And we see an area of 0.0102. So that's our area here, 0.0102. And then do it again for x bar equaling 45. So the z-score, now 45 minus 43.9 over 5.8 over the square root of 50, and that gives 1.34. So check the calculations, make sure you're comfortable with that. And then table 4, once again, gives an area of 0.9099. So that's this area. Okay, so we want everything in between. So the area that we're looking for, or the probability that x bar is greater than 42 and less than 45, because it's everything in between these two values. Remember, we subtract the areas. So always larger minus smaller, 9099 minus 0.0102. And that gives us 0.8997. Alright, so another example to finish off this section. And here we're talking about a bank auditor who's reporting the credit card balances are again normally distributed, so it's always a good thing to read. Just write down the givens off to the side. The mean is 2870 and standard deviation 900. So mu 2870, standard deviation sigma 900. And what is the probability that a randomly selected credit card holder has a credit card balance greater than 3,200? Keyword being a single piece of data. So since we're talking about an individual, piece of data, then the z-score formula is just x minus mu over sigma. And what we want is the probability that x is greater than the 3,200. But note that it's x, not x bar. It's an individual piece of data. So you can draw the distribution. Oh, and last example, I always get so excited I forget to label my z-scores in the chart here. If you want to label them, you can. You don't need to. Okay, but getting back to this example, we'll draw the normal distribution, of course. Mean goes down the middle, 2870. We want the probability that the individual is greater than 3,200. Let me call it right there. It's just x. 3,200. Greater than means everything to the right. So let me extend these a little bit more so we can see it. We want everything in the tail. Everything greater than that 3,200. Now what we're going to need to do is find this area, or this probability. And then in the end, after we find that, we're going to have to subtract from 1, or find its complement to find the area we're looking for. But since we're talking about an individual piece of data, in this case the x is just 3,200. It's just x once again. And our z-score formula is x minus mu over sigma. So that's going to be x was 3,200 minus mu, the 2870, over sigma, 900. And that calculates to be positive 0.37. Let me just double check that. 3,200 minus 2870 equals, divided by the 900. Yeah, 0.3666 repeated. Okay, so then we go to table 4. And that gives us a left cumulative area of 0.6 .443. Alright, so therefore the area we're looking for, again I always say area, you could say probability that x is greater than the 3200 is equal to, okay, because it's to the right, it's 1 minus the area that we just found. So 1 minus the 0.6443 or 3557. Okay, so then the next part is we're randomly going to select 25 credit card holders. So the sample size N is 25, and we want to know what is the probability that their mean, so the mean of a sample, or sample mean, so that's the central limit theorem again, and our z-score formula once again is x bar minus mu over sigma divided by the square root of n. And we're using the same in mu and sigma as in part A. So what we want is the probability that the mean of the sample, x bar, is greater than the 3200. So, draw the diagram. There's a normal distribution. Got the mean going down the middle of 2870 again. This is now x bar. The mean of the sample is 3200. And again, we want everything to the right. So in the right tail, greater than. Alright, but when we look up the area, we get the left cumulative. When we look up the z-score, that is, we get the left cumulative area. And so, let's say for x bar equaling the 3200. Okay, once again, our z-score formula is x bar minus mu, so 3200 minus the mean of 2870 again, but divided by the standard deviation, which was the 900, that's being divided by the square root of n, and n, in this case, was the 25. So, calculating that, get positive 1.83, and so then we go to table 4, and that tells us an area of 0.9664, and so this is the area, 0.9664, and we want everything to the right of that. So the area, or the probability that, once again, x bar is greater than the 3200 is equal to the complement of that area, 1 minus 0.9664, which is 0.0336. Alright, so then just a little question at the bottom. It says the sample mean would or would not be considered unusual because it lies or does not lie within 1, 2, or 3 standard deviations of the mean. Now remember, if it's more than 2, more than positive 2, or less than negative 2, that's unusual. So therefore, since our z-score formula for the sample mean was 1.83, it would not be considered unusual because it lies within 2 standard deviations of the mean, of the sample means. Okay, so that's the end of 5.4, and we'll see you when you're ready for 5.6, or chapter 6. We're going to chapter 6 next.